When we first encounter the atom in our education, we are taught that it is made of three basic parts: protons, electrons, and neutrons. The proton carries a positive charge, the electron a negative charge, and the neutron no charge at all. It seems almost like a convenient balance: one positive, one negative, one neutral. But for physicists and philosophers of science, this arrangement was never merely a coincidence. Why should a particle exist with mass nearly equal to that of the proton, yet with absolutely no electric charge? Why would nature produce such a particle invisible in most everyday interactions, silent in the world of electricity and chemistry, but absolutely indispensable in the architecture of matter? This question touches on a profound mystery of physics, the neutrality of the neutron, and exploring it reveals how deeply interconnected the fabric of the universe truly is. To understand the scientific significance of the neutron's neutrality, one must first grasp how central charge is to our conception of matter. For centuries, long before the neutron was discovered, matter was imagined as being structured by attractive and repulsive forces between positive and negative entities. Electricity, discovered in the 18th century and harnessed in the 19th, seemed to tell a simple story. Positive and negative charges attract like charges repel. When the electron was discovered at the end of the 19th century, its negative charge provided an explanation for electricity at the microscopic level. Or the proton was identified as the positive counterpart. Powerful, this sect of cum-cara connection feels rare. It seemed as though everything about matter could be explained through this interplay of positive and negative charge. But there was a puzzle. If atoms, what are neutrons, contained only protons in their nucleus, then the electrostatic repulsion between these positively charged particles should have torn the nucleus apart. Even hydrogen with its single proton could exist. But how could helium, carbon, oxygen, or uranium ever hold together when they contain 2, 6, 8, or 90? Two protons all fiercely repelling each other. There had to be something else hidden within the nucleus, some unseen force or particle that prevented the nucleus from self-destruction. That missing entity turned out to be the neutron. But when James Chadwick revealed its existence in 1932, what struck scientists most was not merely its presence, but its neutrality. Here was a particle with nearly the same mass as a proton, but completely lacking in electric charge. This was a paradox, because in a universe where charge seemed to govern every interaction from the structure of atoms to the flow of currents in wires, it was puzzling to imagine a massive particle that carried none. And yet that very neutrality was what allowed neutrons to slip unnoticed through matter, to evade electrical forces, and to quietly stabilize atomic nuclei. In a sense, the neutron's most defining feature was what it lacked. Why is this neutrality significant? Imagine for a moment that neutrons carried even the tiniest charge. Suppose they were slightly positive. In that case, they would add to the electrostatic repulsion inside the nucleus, making it impossible for atoms larger than hydrogen to exist. The universe would be robbed of all complex matter, all chemistry, all biology. Alternatively, if neutrons were slightly negative, they would be drawn toward protons with immense force, collapsing the nucleus into a dense knot without the possibility of stable isotopes. The periodic table as we know it would vanish, and with it the diversity of matter. In both cases, the balance of the cosmos would be ruined. The neutrality of the neutron is not an accident. It is the key to why atoms can exist in their current form. It ensures that the strong nuclear force, the mysterious glue of the nucleus, can act without interference from electrostatic forces. Neutrality makes the neutron an invisible architect of stability. The significance of this neutrality is also evident in the way neutrons interact with the world around them. Because they carry no charge, neutrons do not feel the pull or push of electric fields, nor are they deflected by magnetic fields in the way charged particles are. This makes them extraordinarily difficult to detect, which is why it took so long for physicists to confirm their existence. But this same elusiveness makes them perfect for penetrating matter, slipping past the electric barriers that confine protons and electrons. In nuclear reactions, this property becomes especially important. A neutron can approach a nucleus without being repelled, unlike a proton which is forced back by the electric repulsion of the positively charged nucleus. This allows neutrons to act as triggers in nuclear processes. From the fusion reactions in stars to the chain reactions in nuclear reactors, in both nature and technology, their neutrality makes them the silent instigators of transformation. The neutrality of neutrons is also bound to their deeper structure. We now know that protons and neutrons are not truly elementary, but are made up of quarks held together by the strong force. A proton contains 2 up quarks and 1 down quark, giving it a net positive charge. A neutron, in contrast, contains 1 up quark and 2 down quarks whose charges cancel out exactly, leaving no net charge. But this explanation, while correct mathematically, does not fully answer the deeper question. Why should nature choose this exact configuration of quarks, giving rise to one particle charged and another neutral? Here we encounter one of the great mysteries of physics. The universe could in principle have been built differently with different fundamental charges, different masses, different balances. And yet it is not. The neutron neutral and massive exists precisely as it must in order for stable matter to form. When we consider the neutron's neutrality in a broader scientific context, it takes on even more significance. In the early universe, just after the Big Bang, neutrons were formed in nearly equal numbers with protons. As the universe cooled, many neutrons decayed, but those that remained were captured into atomic nuclei during a process known as nucleointhesis. Their neutrality was vital. Had neutrons been charged, they could not have bound with protons to form helium, the second most abundant element in the cosmos. Without helium, there would be no stars burning through fusion, no heavier elements forged in stellar cores, and no planets or living beings to ponder these questions. The neutrality of the neutron is woven into the history of the cosmos itself. It is not merely a feature of the mystery of no-charge particle physics, but a precondition for cosmic evolution. This neutrality also brings with it profound scientific opportunities. Because neutrons are uncharged, scientists can use them as probes to explore matter in ways that charged particles cannot. Neutron scattering experiments developed in the 20th century allow us to map the arrangement of atoms in solids and liquids, to understand magnetic structures, and to uncover the secrets of materials at the quantum level. In medicine, neutrons are used in cancer treatments, exploiting their ability to penetrate tissues without being deflected by charges. In nuclear reactors, neutrons serve as both catalysts and regulators of energy production. In each case, their neutrality is the property that makes them indispensable. At a deeper philosophical level, the neutrality of the neutron reminds us of the subtlety of nature's design. Human intuition often expects balance to be achieved through opposites: positive versus negative, matter versus antimatter, attraction versus repulsion. But here, balance is achieved not by opposition, but by absence. The neutron's neutrality is not a void. It is a hidden power and enabling condition. It allows the proton to be what it is, the electron to be what it is, and yet for the atom to exist beyond the clash of charges. It is the quiet middle ground, the mediator of forces. Without it, the universe would tip into chaos. And so when we ask why neutrons carry no charge, we are not simply asking a technical question of particle physics. We are asking why the universe is constructed in a way that permits stability, complexity, and life. The neutrality of the neutron is not only a scientific curiosity, but a cosmic necessity. It allows the nucleus to hold together, the elements to form, and the stars to shine. Its hidden role is written into every breath of air, every drop of water, every living cell. To overlook the significance of its neutrality would be to overlook the very conditions of existence. Let us begin by revisiting the nucleus. Inside that unimaginably dense core of the atom, protons are constantly repelling one another. The strong nuclear force, far greater in intensity than the electric force, but limited in range to distances smaller than the width of a proton, holds them together. Neutrons participate in this binding, strengthening the cohesion without adding to the electric repulsion. Their neutrality is precisely what allows them to act as structural supports. To use an architectural metaphor, if protons are like columns pushing against one another, neutrons are like invisible beams that hold them steady. Remove the beams or give them charges that upset the balance and the structure collapses. The entire table of elements which underlies chemistry, biology, and geology would vanish. This fact leads to one of the most fascinating insights. Neutrality is creative. We tend to think of neutrality as absence, as the lack of action or property. But in the case of neutrons, neutrality is not absent. It is the enabling condition of presence. Without neutrality, atoms could not exist in the form they do. With it, the universe blossoms into complexity. This inversion of meaning is profound. A lack becomes a force of creation. A zero becomes the key to everything. To see how this neutrality plays out in detail, consider isotopes. Carbon, for example, exists in nature and forms with 6, 7, or 8 neutrons. These different isotopes have identical chemical behavior, since chemistry depends on the number of protons and electrons, but their physical stability varies drastically. Carbon-12 with 6 neutrons is stable and forms the backbone of organic life. Carbon-14 with 8 neutrons is unstable and decays, releasing radiation that scientists use for dating ancient artifacts. Here again, it is the neutron count and the neutrality that allows neutrons to sit quietly in the nucleus without disrupting electric balance that determines the difference between permanence and decay, between the structure of life and the measure of time itself. We can extend this reasoning to the stars. In the heart of a star, hydrogen nuclei fuse to form helium. This process depends not only on protons, but on the availability of neutrons to balance the new nuclei. If neutrons carried a charge, nuclear fusion would falter and stars could not produce the heavier elements that seed planets and living organisms. The neutrality of the neutron is thus encoded into the fiery engines of the cosmos. The gold in a wedding ring, the calcium in bones, the oxygen in the air, all were forged in stellar furnaces where neutrons through their neutrality made possible the alchemy of element building. When stars die in supernova, the abundance of neutrons they release allows for the rapid creation of elements far heavier than iron, scattering them into space and eventually into our bodies. Neutrality is therefore not only a stabilizer but also a generator, a participant in the cosmic symphony that builds the ingredients of life. There is also a temporal dimension to this story. Neutrons outside the nucleus are unstable, decaying in about 15 minutes. Quark structure explained into a proton, an electron, and a nearly massless antitrino. Inside the nucleus, however, they can remain stable indefinitely. Why? Because their neutrality allows them to evade the forces that otherwise destabilize them. This curious duality, unstable in isolation, stable in partnership, reminds us that neutrality is not merely a static feature, but a relational one. It exists in context. The neutron's neutrality allows it to adapt, to be fragile in one environment and enduring in another. That adaptability is crucial for both the birth of the universe and the evolution of its structure. At the level of fundamental physics, the neutrality of the neutron raises further puzzles. Neutrons, though uncharged, are not devoid of internal structure. They are built of quarks whose fractional charges sum to zero. This raises the question, why do these particular arrangements of quarks exist in nature? Why do the fundamental constants of physics allow this exact balance, producing a particle with no net charge, but with just enough mass to counterbalance protons? If neutrons were slightly heavier than they are, all would have decayed before atoms could form in the early universe. If they were slightly lighter, protons might have decayed into neutrons, leaving no hydrogen and no water. The neutrality and mass of the neutron are finely tuned for the emergence of a habitable cosmos. Some scientists see in this a case of the anthropic principle. The universe appears to be arranged in such a way that life is possible, and the neutrality of the neutron is one of its most delicate arrangements. From a practical standpoint, humanity has learned to harness the power of neutrons precisely because of their neutrality. Nuclear reactors rely on neutrons to sustain chain reactions. A free neutron striking a uranium nucleus can split it into fragments while releasing more neutrons. These new neutrons continue the process, creating a cascade of energy. If neutrons carried charge, they could not penetrate the positively charged uranium nucleus to trigger this reaction. The neutrality of the neutron is what makes nuclear power and nuclear weapons possible. In medicine, beams of neutrons are used to target tumors, where their ability to penetrate tissues without being deflected by charges makes them uniquely effective. In science, neutron scattering has revolutionized our knowledge of materials, allowing us to map magnetic properties, crystalline structures, and quantum behaviors invisible to other probes. Each of these applications rests on the neutron's defining trait, neutrality. But neutrality is not only a scientific feature, it is also a metaphorical one. When physicists speak of the neutron, they describe a particle that stands between the polarities of charge, neither one nor the other, and yet vital to the existence of both. In this sense, the neutron represents balance, the quiet middle path that enables the extremes to coexist. This metaphor resonates beyond physics, reminding us that in life as in matter, it is often the unseen neutral ground that allows the charged opposites to endure without collapse. It is tempting, of course, to see all this as inevitable, as if neutrons were destined to be neutral. But the deeper truth is that neutrality is fragile. The tiniest deviation would have changed everything. If the balance of quarks inside neutrons had been altered, or if the laws of physics had been slightly different, there would be no stable nuclei, no periodic table, no stars or planets. The very possibility of asking why neutrons are neutral depends on their neutrality being exactly what it is. This recognition transforms the question into something larger. Not merely why are neutrons neutral, but why does the universe permit neutrality at all? Perhaps the answer lies in symmetry. In the grand theories of physics, symmetry plays a central role. The existence of particles with opposite charges, the conservation of energy and momentum, the invariance of laws across time and space, all are rooted in symmetry. The neutron's neutrality may be one expression of such symmetry, a reflection of deeper patterns in the quantum fabric of reality. It is as though the neutron embodies the principle that balance is not an exception, but a rule of nature. To be neutral is to participate in the deepest law of all, that the universe seeks equilibrium, even as it gives rise to diversity. And so when we stand back and survey the story, we see that the neutrality of the neutron is far more than a particle property. It is a cosmic principle without which the architecture of matter would collapse. It is a bridge between the smallest scales of quarks and the largest scales of galaxies. It is a condition that has made possible the formation of atoms, the ignition of stars, the chemistry of life, and the very consciousness that now reflects upon it. To ask why neutrons carry no charge is in the end to ask why the universe is the way it is. Why there is something rather than nothing. Why existence holds together instead of flying apart. The neutron's neutrality is not loud. It does not dazzle like the lightning bolt of an electron or the magnetic embrace of a proton. It is quiet, invisible, hidden. But it is precisely in that quietness that its power lies. By carrying no charge, the neutron carries the possibility of everything. Without it, there would be no atoms, no stars, no life. With it, the universe endures. Neutrality, once thought to be nothing, is revealed as the greatest something of all. In the early decades of the 20th century, physics was in turmoil. The atom, once imagined as the smallest indivisible building block of matter, had already revealed layers of unsuspected complexity. The electron had been discovered in Thought 197 by J.J. Thomson, shattering the idea that atoms were indivisible. Ernest Rutherford's gold foil experiment of 19111 showed that atoms contained a dense, positively charged nucleus at their heart surrounded by a cloud of negatively charged electrons. By the 1920s, the proton was recognized as the positively charged component of the nucleus, balancing the electron's negative charge and giving each atom its unique identity. But despite this progress, Something was still missing. The mathematics of atomic masses did not add up, and the theory of the atom was full of unresolved tensions. Into this atmosphere of uncertainty stepped James Chadwick, whose 1932 discovery of the neutron transformed atomic theory and reshaped physics forever. To understand why the neutron's discovery was so revolutionary, one must first picture the state of atomic theory before it appeared. Scientists had already established that the number of protons in an atom's nucleus, its atomic number, determined the element. Hydrogen had 1 proton, helium 2, lithium 3, and so on up the periodic table. This explained why elements were arranged as they were, but it did not explain their masses. A helium atom, for instance, had 2 protons, and yet its mass was roughly 4 times that of hydrogen. Where did the extra weight come from? Physicists hypothesized that additional particles were lurking inside the nucleus, but their nature remained obscure. One popular theory was that nuclei contained not only protons, but also electrons. This seemed plausible because it would explain how heavier elements could exist without accumulating too much positive charge. For example, nitrogen with an atomic number of 7 might have been imagined as consisting of 14 protons and 7 nuclear electrons, canceling out enough positive charge to leave only 7 net positive charges. This, however, was problematic. Electrons were extremely light compared to protons, and cramming them into the dense confines of a nucleus did not fit with quantum mechanics, which by the late 1920s was already reshaping physics. Nuclear electrons could not account for observed nuclear properties, nor could they explain certain experimental results. Something new was needed. Hints of a missing particle came from experiments in the 1920s and early 1930s. Physicists bombarded light elements such as beryllium with alpha particles and neutrons vs protons, observed the emission of highly penetrating radiation. At first, this radiation was thought to be gamma rays, a type of high-energy electromagnetic wave. But the radiation behaved oddly. When it struck paraffin wax, a substance rich in hydrogen, it ejected protons with unexpectedly high energy. Gamma rays could not account for this effect. There had to be another explanation. James Chadwick, a reserved but determined British physicist working at the Candish Laboratory in Cambridge, took up the puzzle in 1932. He suspected that the mysterious radiation from beryllium was not electromagnetic at all, but consisted of a new type of particle. He designed experiments to test this idea, carefully measuring the energies of recoiling protons and comparing them with theoretical predictions. After meticulous analysis, Chadwick concluded that the radiation was made of particles with a mass roughly equal to that of protons, but with no electric charge. He had discovered the neutron. This discovery was nothing short of a revolution. At once, it solved the riddle of atomic masses. The mass of a nucleus could now be understood as the sum of its protons and neutrons, rather than protons and hypothetical nuclear electrons. Helium, for example, with 2 protons and 2 neutrons had a mass about 4 times that of hydrogen, exactly as observed. Suddenly, the bookkeeping of atomic masses made sense, and the theory of isotopes, atoms of the same element differing in mass, could be fully explained. Carbon-12 and carbon-14, both with 6 protons but differing numbers of neutrons, were now understood as isotopes. But Chadwick's discovery did far more than tidy up atomic arithmetic. It opened entirely new avenues of inquiry. By showing that the nucleus was made of 2 kinds of particles, protons and neutrons, the discovery gave physicists a new framework for understanding nuclear forces. Protons alone could not be the whole story, for their mutual repulsion would make nuclei impossible. The existence of neutrons suggested a new balance of forces, a nuclear glue that could hold protons together without contributing to electric repulsion. This insight was a decisive step toward the later development of the theory of the strong nuclear force, one of the 4 fundamental interactions of nature. Moreover, neutrons themselves became powerful tools for probing matter. Because they carried no charge, they could penetrate nuclei without being deflected by electric fields. This made them uniquely suited to initiating nuclear reactions. Within a few years of Chadwick's announcement, Scientists such as Enrio Fermi were using neutrons to bombard elements and produce new isotopes. Neutrons could slip into nuclei more easily than protons or alpha particles, making them perfect projectiles for exploring nuclear processes. This line of research would ultimately lead to the discovery of nuclear fission, and with it the dawn of the atomic age. The impact of Chadwick's work was recognized immediately. In 1935, he was awarded the Nobel Prize in Physics for the discovery of the neutron. Yet even then, the full implications of his discovery were only beginning to unfold. For theoretical physics, it forced a complete rethinking of the atom's structure. For experimental physics, it provided a new tool of unprecedented power. And for the world, it opened both the promise of nuclear energy and the peril of nuclear weapons. It is worth pausing to appreciate the intellectual courage required for Chadwick's achievement. In 1932, the idea of a neutral particle inside the nucleus was not obvious. The reigning theories still clung to the notion of nuclear electrons. To propose and prove the existence of an entirely new particle required both boldness and rigorous experimental design. Chadwick's methodical approach by barding elements, measuring recoils, eliminating alternative explanations, was a model of scientific reasoning. He transformed a puzzling anomaly into a clear discovery, demonstrating how empirical evidence can reshape theory. The discovery also illustrates a broader theme in the history of science: the importance of the unseen. Neutrons were invisible, undetectable by ordinary means, and left no track in detectors that revealed charged particles. Yet their effects could be inferred through careful observation. In this sense, the neutron represents the power of indirect reasoning in science. We often learn about the world not by seeing things directly, but by observing their influence on what we can see. Just as the existence of planets beyond Neptune was inferred from gravitational anomalies, so too was the neutron revealed through its hidden impact on experimental results. By the mid-1930s, the neutron had become an accepted part of physics, but its discovery continued to reverberate. It forced new questions about the fundamental constituents of matter. What held protons and neutrons together inside the nucleus? Why did some combinations of protons and neutrons produce stable nuclei, while others were unstable? Why were neutrons stable inside nuclei but unstable outside, decaying into protons and electrons? These puzzles drove decades of research, culminating in the development of quantum chromodynamics, the theory of quarks and gluons, in the latter half of the 20th century. Chadwick's discovery also intersected with the great social and political currents of the time. In the 1930s, Europe was sliding toward war. The realization that neutrons could induce nuclear reactions led directly to research on nuclear fission. When Otto Hahn and Fritz Strassmann discovered fission uranium in 1938, they did so by bombarding uranium nuclei with neutrons. Without neutrons, the chain reactions that power nuclear reactors and atomic bombs would be impossible. Thus, the neutron discovered in a quiet laboratory in Cambridge became central to the most destructive and transformative technology of the 20th century. At the same time, the neutron's discovery enriched peaceful science. Neutron scattering, developed in the mid-20th century, became one of the most powerful techniques for studying the structure of matter. By analyzing how neutrons scatter when they pass through crystals or liquids, scientists could determine atomic arrangements with extraordinary precision. This technique has been crucial in fields as diverse as chemistry, biology, and materials science. It has helped reveal the structures of proteins, the dynamics of magnetic materials, and the properties of superconductors. All of this traces back to Chadwick's 1932 breakthrough. The neutron's discovery also reshaped education. By the 1940s, textbooks no longer described nuclei as proton-electron systems, but as proton-neutron systems. The simple model of the nucleus as a collection of protons and neutrons became the foundation of nuclear physics education. Even as more complex theories were developed, for generations of students, the image of the nucleus as a proton-neutron assembly has been their entry point into the mysteries of matter. And yet, beneath all the scientific and technological consequences, The discovery of the neutron carries a philosophical weight. It reminds us that reality often hides essential features beneath the surface. For decades, physicists believed they understood the atom. Then came the neutron, invisible and unsuspected, overturning assumptions and forcing a new vision. This pattern, the discovery of the neutron, did not simply add a new particle to the catalog of known entities. It forced scientists to reimagine the entire structure of matter. Before Chadwick's work, atomic theory had already undergone several revolutions. Dalton's indivisible atoms of the 19th century had given way to Thomson's plum pudding model, which in turn had been replaced by Rutherford's nuclear atom, refined by Bohr into quantized orbits. Each shift had dismantled a layer of assumption, but the neutron's arrival in 1932 was different. It was not just a new model, but a new reality that demanded physics itself be rebuilt. One of the first consequences of the discovery was a clearer understanding of isotopes. Isotopes had puzzled chemists since Frederick Soddy introduced the term in 1913. How could two atoms of the same element behave identically in chemistry yet differ in mass? With neutrons in the picture, the answer became simple. Isotopes differ in their number of neutrons. Oxygen-16, oxygen-17, and oxygen-18 all have 8 protons, giving them the same chemical identity. But different neutron counts explain their varying masses. This breakthrough brought coherence to chemistry and physics, uniting two disciplines that had sometimes seemed separate. For the first time, the periodic table and atomic mass were harmonized by a deeper structure. Another consequence was the realization that nuclear forces must be fundamentally different from electric forces. Protons alone could not bind. Their positive charges would repel each other violently. Neutrons, however, could coexist with protons without adding to the electrostatic repulsion, suggesting that some new charge-independent force was at work. This recognition paved the way for Hayakawa's 1935 theory of Meson exchange, which proposed that protons and neutrons were bound together by the exchange of particles. Yukawa's theory anticipated the discovery of the pion and laid the foundation for what later became quantum chromodynamics. None of this could have unfolded without the neutron's discovery. The neutron also forced scientists to reconsider the problem of nuclear stability. Why were some nuclei stable and others unstable? Why did certain isotopes decay by emitting electrons or beta particles, while others did not? The neutron provided a new lens for these questions. In beta decay, a neutron inside the nucleus transforms into a proton, emitting an electron and an antitrino. This process explained the source of nuclear electrons that earlier models had mistakenly placed inside the nucleus. The neutron thus clarified not only the structure of stable matter, but also the mechanisms of radioactive decay. Chadwick himself was deeply aware of the potential implications of his discovery. In the years after 1932, he collaborated with colleagues in Britain and abroad to explore neutron-induced reactions. These experiments revealed the extraordinary potential of neutrons to trigger transformations in nuclei. Because neutrons carried no charge, they could penetrate the electric barriers that repelled protons than alpha particles, making them far more effective projectiles. Enrio Fermi's experiments in Rome in the mid-1930s took this principle to new heights. By bombarding uranium with neutrons, Fermi and his team inadvertently set the stage for the discovery of nuclear fission. The chain of discovery is striking. Chadwick's neutron led to Fermi's neutron bombardments, which led to Hahn and Stremann's discovery of fission in 1938, which in turn led to the Manhattan Project and the atomic bomb in 1945. In just over a decade, an invisible particle discovered in a Cambridge laboratory reshaped the destiny of nations and the trajectory of history. The neutron is a stark reminder that pure science pursued for curiosity can unleash consequences beyond imagination. Role in nuclear stability. Yet alongside its destructive potential, the neutron became a tool of creation and healing. In nuclear reactors, neutrons sustained the controlled chain reactions that provide power to cities. In medicine, neutron therapy has been used to target deep-seated tumors, exploiting their penetrative ability. In industry, Neutron imaging allows engineers to peer inside materials without damaging them. In archaeology, neutron activation analysis can reveal the composition of ancient artifacts with exquisite precision. The neutral particle born in the depths of the nucleus has become a quiet servant of civilization. The neutron also deepened the mystery of the universe's origins. In the first minutes after the Big Bang, the universe was a sting soup of protons, neutrons, electrons, and photons. As it cooled, neutrons combined with protons to form the first nuclei. Without neutrons, only hydrogen could exist, and the universe would lack the helium and heavier elements needed for stars and planets. Thus, the discovery of the neutron was not merely an advance in laboratory science. It was the unveiling of a cosmic truth. The very existence of galaxies, worlds, and life depends on neutrons. To recognize their role is to glimpse the deep interconnection between microphysics and the universe at large. From a philosophical perspective, the discovery of the neutron reflects the recurring theme of hiddenness in science. For decades, physicists tried to explain atomic masses and nuclear stability without ever seeing the neutron. Its invisibility was both its greatest challenge and its greatest power. When Chadwick revealed it, the world saw how much had been missing from the picture. The lesson is timeless. What we cannot see may be more important than what we can. The neutron is the archetype of hidden influence, unseen yet decisive. Another philosophical lesson arises from the neutron's neutrality. In a world of opposites, positive and negative, attraction and repulsion, the neutron is the mediator. Its discovery showed that reality is not always about polarity. Sometimes the absence of charge, the neutral middle, is the key to balance. This insight resonates beyond physics, hinting at a universal principle. Stability often requires something that stands apart from extremes, something neutral. In the neutron, science found not just a particle, but a metaphor for harmony. As the 20th century advanced, the neutron's role in particle physics evolved. By the 1960s and 1970s. The quark model revealed that neutrons, like protons, are not elementary particles, but composites of smaller constituents. The neutron's neutrality arises from a delicate balance of quark charges. 2 down quarks each with a charge of 1/3 and 1 up quark with a charge of 2/3. The total adds to 0. This discovery added another layer to the neutron's significance. Neutrality, once an unexplained fact, became a consequence of deeper symmetries in the subatomic world. Even today, research into neutrons continues to push boundaries. Experiments seek to measure whether the neutron has an electric dipole moment, a tiny imbalance that would reveal new physics beyond the standard model. Others study the precise lifetime of free neutrons, probing the balance between matter and antimatter in the early universe. The neutron, though discovered nearly a century ago, still holds secrets that could reshape our understanding of reality. When historians of science look back on the 20th century, they see Chadwick's discovery as a watershed moment. It was the last of the great discoveries of the classical atomic particles, completing the triad of proton, electron, and neutron. It brought closure to decades of speculation while opening vast new horizons. Its impact stretched from the laboratory to the battlefield, from the power plant to the hospital, from the nucleus of the atom to the birth of the cosmos. Few discoveries have had such wide-ranging consequences. And yet at its heart, the discovery of the neutron is a human story. It is the story of a quiet English physicist working in a modest laboratory, piecing together evidence from puzzling experiments. It is the story of persistence, of refusing to accept unsatisfactory explanations, of daring to propose a new kind of particle when none had been imagined. It is the story of science itself. Curiosity, evidence, and imagination reshaping our view of the world. The impact of the neutron's discovery on atomic theory was profound. No longer could the nucleus be thought of as a simple cluster of protons. No longer could atomic mass be dismissed as an unsolved anomaly. With the neutron, the nucleus became a dynamic, balanced system of two kinds of particles, governed by forces more subtle than electricity. The atom, once a symbol of simplicity, was revealed as a realm of hidden complexity, and in that revelation lay the seeds of modern, nuclear physics. As we reflect today, nearly a century after 1932, we can see how Chadwick's discovery resonates across disciplines and generations. It reminds us that the universe is full of hidden dimensions waiting to be uncovered. It reminds us that the smallest discoveries can have the greatest consequences. And it reminds us that neutrality, often overlooked, can be the most powerful property of all. The neutron stands as both particle and principle, invisible, neutral, essential. Its discovery was not only a milestone in atomic theory, but a turning point in human understanding of the cosmos. When we look at the atom, it is tempting to imagine that the tiny nucleus at its center is a simple and self-evident structure. Protons clumped together, their positive charges defining the element, while electrons hover around in their orbits. But the truth of the matter is far more delicate and astonishing. The nucleus is not just a bundle of protons. It is a finely tuned arrangement of protons and neutrons. And it is this hidden interplay that allows matter itself to exist in the form we know. Without neutrons, there would be no stability, no structure, no chemistry, and ultimately no life. The story of the neutron as a stabilizer of the atomic nucleus is therefore one of the most profound tales in the history of science. A reminder that the very foundation of the universe depends on a balance of forces invisible to our eyes. To understand the role of neutrons, we must first confront the mystery of how the nucleus exists at all. Imagine packing protons, each carrying a positive electric charge, into a tiny region only a few femtometers across. According to Coulomb's law, like charges repel each other with a force that grows stronger the closer they come. In the nucleus, protons are pressed unimaginably close together. If only electrostatic forces were at play, the nucleus would simply fly apart, its protons hurling away from each other, like magnets forced back. And yet the nucleus does not explode. It holds together. The reason lies in the existence of neutrons. Neutrons carry no electric charge, which might suggest at first glance that they are passive bystanders in the nucleus. But their neutrality is not a sign of irrelevance. Rather, it is the secret to their stabilizing role. Neutrons interact with protons and with each other through the strong nuclear force, the most powerful of nature's fundamental forces, which binds nucleons, protons, and neutrons together. This force is immensely attractive at short distances, far outweighing the repulsion of electric charges. Crucially, it does not discriminate between protons and neutrons. It binds both equally. This symmetry allows neutrons to act as the glue of the nucleus, providing attraction without adding to the burden of repulsion. The metaphor often used is that neutrons are like mediators in a quarrel. The protons in the nucleus want to push each other apart, their charges clashing in a constant struggle. The neutrons step in, offering the same binding embrace of the strong force, but without contributing to the conflict of charge. They balance the system, holding the quarreling protons together, ensuring that the nucleus remains intact. Without these mediators, only hydrogen, the single proton atom, could exist. The entire periodic table with its wondrous diversity of elements depends on neutrons performing this hidden role. The balance between protons and neutrons, however, is not simple or fixed. In the lighter elements, stability is often achieved when the number of protons and neutrons is roughly equal. Carbon with 6 protons and 6 neutrons is stable. Oxygen with 8 of each is also stable. But as nuclei become larger and heavier, the increasing electrostatic repulsion between protons demands additional neutrons to compensate. Lead, for instance, with 82 protons requires 126 neutrons to remain stable. The neutron-proton ratio is not arbitrary but evolves as the size of the nucleus grows. It is as if the nucleus must continually adjust its balance sheet, adding more and more neutrons to counteract the mounting pressure of protonic repulsion. This delicate balancing act explains the phenomenon of nuclear stability and instability. When the ratio of protons to neutrons falls out of harmony, the nucleus becomes unstable and undergoes radioactive decay to correct itself. If there are too many neutrons, one may transform into a proton via beta decay, releasing an electron and an antineutrino. If there are too few neutrons, the nucleus may undergo other processes to restore equilibrium. In every case, the underlying logic is the same. Stability depends on the right proportion of neutrons to protons. The neutron is not an accessory but a central player in the drama of nuclear existence. The role of neutrons as stabilizers can also be appreciated historically in the understanding of isotopes. Isotopes are simply different versions of the same element sharing the same number of protons but differing in their number of neutrons. Some isotopes are stable, others radioactive. The difference lies in how effectively the neutrons can balance the forces in the nucleus. Consider uranium with its isotopes uranium-2 and uranium-338. Both have 92 protons, but one has 143 neutrons and the other 146. Those few extra neutrons determine whether the isotope can sustain a nuclear chain reaction, whether it decays slowly over billions of years, or whether it is file and explosive. The destiny of an element, even the fate of entire nations in the nuclear age, can hinge on how neutrons perform their stabilizing function. On a more microscopic scale, physicists have discovered that the stabilizing role of neutrons is not simply about counting numbers, but about the complex shell structure within the nucleus. Just as electrons in atoms occupy shells that define chemical behavior, protons and neutrons in the nucleus occupy nuclear shells governed by quantum mechanics. Certain magic numbers of protons or neutrons 2A, 20, 28, 50, 82, and 126 confer extraordinary stability, much like noble gases in the periodic table. The filling of these, the strong force connection nuclear shells, depends critically on the interplay between protons and neutrons, further emphasizing that neutrons are not passive fillers, but active architects of nuclear order. Beyond the stability of individual nuclei, neutrons also shape the cosmic abundance of elements. In the hearts of stars, nuclear fusion builds heavier elements from lighter ones. These processes are profoundly dependent on neutron balance. In stellar nucleosynthesis, neutrons serve as stepping stones that allow nuclei to climb the ladder of atomic weights. The slow capture of neutrons known as the S process and the rapid capture of neutrons, the R process, are responsible for creating nearly all the elements heavier than iron. Gold, platinum, uranium, all the treasures of the Earth owe their existence to neutrons playing their stabilizing role in the violent furnaces of stars and the cataclysmic explosions of supernova. Without neutrons, the universe would be stripped of its richness, a barren place of hydrogen and helium. Even the free neutron, which exists only briefly outside the nucleus, offers clues about stability. A neutron unbound to a nucleus decays in about 15 minutes, transforming into a proton, electron, and antneutrino. This instability might seem to undermine its role, but in fact it reinforces the lesson. Neutrons are meant to live in partnership with protons, not in isolation. Their true function is realized only within the nucleus, where their balancing force becomes essential. The contrast between the instability of the free neutron and the stabilizing power of the bound neutron underscores the deep interdependence of matter's building blocks. At the human level, the stabilizing role of neutrons is not just a scientific curiosity, but a practical reality that touches our lives. Nuclear medicine, which relies on isotopes for imaging and therapy, depends on the neutron-to-proton balance in nuclei. Nuclear energy, which harnesses fission reactions, is fundamentally a manipulation of neutron balance to control stability and instability. Even carbon dating, the tool archaeologists use to probe the past, is possible because neutrons in the atmosphere transform nitrogen into radioactive carbon-14, which then decays in a predictable way. From energy to medicine to history, the quiet stabilizer in the nucleus influences the course of human culture. The neutron's role also invites us to think about balance as a principle of existence. In a world often described in terms of opposites, light and dark, positive and negative, the neutron symbolizes the necessity of the middle path, neither charged nor empty, neither weak nor irrelevant. The neutron demonstrates that neutrality can be the very foundation of stability. It suggests that sometimes the greatest strength lies not in exerting force, but in harmonizing forces already at play. In this sense, The neutron is not only a particle of physics, but a lesson in philosophy. To appreciate the neutron fully, one must recognize that its stabilizing role is both local and cosmic. Locally, it keeps nuclei intact, allowing atoms to exist. Cosmically, it drives the synthesis of elements, enabling the universe to evolve complexity. The quiet particle that carries no charge turns out to carry the burden of existence itself. To overlook its contribution is to miss the key to why matter holds together. It is as if the neutron hides in plain sight, performing its task without fanfare, ensuring that the universe remains whole. To continue our exploration of how neutrons stabilize the atomic nucleus, we must step deeper into the subtle dance of forces that act at the heart of matter. While the strong nuclear force provides the ultimate glue binding protons and neutrons, the specific contribution of neutrons lies in their ability to dilute the fierce electric repulsion between protons while still participating fully in the attractive nuclear interactions. They are the balancing weights on the cosmic scale, and their presence defines the line between stability and decay. When scientists first began to map the chart of nuclides, the table of all known isotopes, they quickly noticed a striking pattern. Stable nuclei are not scattered randomly, but occupy a narrow band of neutron-to-proton ratios. For lighter elements, the line of stability runs close to 1:1. But as elements grow heavier, the line bends upward, demanding ever more neutrons. This valley of stability reflects the neutron's compensatory role. Too few neutrons and the proton's repulsion overwhelms the nucleus, causing it to undergo proton emission or positron decay. Too many neutrons and the nucleus tips in the opposite direction, becoming unstable to beta decay. Stability, therefore, is not an accident, but a finely tuned balance mediated by the neutron. Consider calcium as an example. Calcium-40 with 20 protons and 20 neutrons is one of the most stable nuclei in nature, doubly magic, because both proton and neutron shells are filled. But calcium-48 with 28 neutrons is also stable. Despite the apparent neutron excess, this isotope reveals another layer of the neutron's role. By filling higher nuclear shells, neutrons can enhance stability even when they seem superfluous. Calcium-48 is so stable that it resists decay for billions of years, serving as a laboratory for scientists to probe the behavior of exotic matter. The lesson is that neutrons do not merely pad the nucleus with neutrality. They sculpt its very architecture, shaping the quantum shells that confer durability. The influence of neutrons on stability extends into the realm of nuclear decay. Take beta decay, where a neutron inside the nucleus transforms into a proton. At first glance, this may seem paradoxical. How can neutrons stabilize the nucleus if they are themselves unstable in isolation? But here lies one of nature's paradoxical symmetries. Inside the nucleus, neutrons live not for minutes, but effectively forever, held in place by the strong force and balanced by their proton companions. Only when the ratio of neutrons to protons deviates from the optimal line of stability do they undergo transformation. In this way, decay itself is not a flaw in the neutron's role, but a mechanism of correction, a way for the nucleus to realign itself with the balance that ensures longevity. In heavy nuclei such as uranium, the stabilizing role of neutrons becomes even more apparent. Uranium-238 with its 92 protons requires a staggering 146 neutrons to remain bound. Without this neutron cushion, the sheer electrostatic repulsion of so many protons would tear the nucleus apart. Even so, uranium-238 is not fully stable. It decays slowly with a half-life of 4–5 billion years. Its file cousin uranium-235 is only slightly different, 3 fewer neutrons. Yet that small shift makes it capable of sustaining a chain reaction when struck by an extra neutron. The fate of nuclear energy and nuclear weapons hinges on the fine arithmetic of neutron numbers. The stabilizer of the nucleus is also the orbiter of power on Earth. To appreciate how neutrons work as stabilizers, we must also understand the strong nuclear force more deeply. Unlike gravity or electromagnetism, the strong force is not infinite in range. It is effective only at distances comparable to the size of a nucleus or around a femtometer. Within that range, however, it is immensely attractive, overpowering the electric repulsion between protons. Neutrons extend the reach of this force by adding more partners to the nuclear binding. Each neutron acts as an anchor point, sharing its strong force attraction with neighboring protons and neutrons alike. The result is a web of bonds that ties the nucleus together. Without neutrons, protons would be left alone in their mutual repulsion, unable to form stable structures beyond hydrogen. The neutron's stabilizing role takes on cosmic significance when viewed in the life cycles of stars. In stellar cores, hydrogen nuclei fuse to form helium, releasing energy that sustains the star. But to move beyond helium and create heavier elements, neutrons become essential. Through neutron capture processes, nuclei climb the ladder of the periodic table, stabilizing themselves with each added neutron. The slow capture process, or S process, occurs in the relatively gentle conditions of aging stars where neutrons are added one at a time over long time scales. The rapid capture process, or AR process, occurs in explosive events such as supernova or neutron star mergers where torrents of neutrons flood nuclei, building heavy elements in seconds. In both cases, neutrons dictate which nuclei can survive the cosmic furnace and which will decay away. The gold in our jewelry, the iodine in our bodies, the uranium in our reactors, all trace their origins to neutrons stabilizing nuclei in the depths of stars. Neutrons also determine the boundary of existence itself, the so-called drip lines of the nuclear landscape. As scientists create exotic isotopes and accelerators, they find that nuclei can only hold so many protons or neutrons before they become unbound. Add one neutron too many and it drips out, unable to remain attached. Remove one neutron too many and the nucleus falls apart. The neutron drip line marks the edge of nuclear matter, the frontier where stability gives way to instability. By mapping these boundaries, physicists are charting not only the role of neutrons, but the limits of matter itself. At the same time, the neutron stabilizing function reveals itself in nuclear reactions here on Earth. In reactors, the chain reaction is governed by the careful balance of neutrons. Each fission event releases additional neutrons, which must then strike new nuclei to sustain the reaction. Too many neutrons and the reaction runs away, producing an explosion. Too few and the reaction fizzles. Reactor control rods made of materials that absorb neutrons are the tools by which engineers manage this balance. Once again, the neutron is the fulcrum of stability. This time not only inside the nucleus, but in the hands of humanity. Even in the domain of biology, the stabilizing role of neutrons has echoes. The elements that compose life, carbon, nitrogen, oxygen, phosphorus, are stable because their nuclei have the right mix of neutrons and protons. The chemistry of life depends on nuclei that persist for billions of years, immune to spontaneous decay. If neutrons did not stabilize these nuclei, living systems could never form. In this sense, the neutron's role is not abstract physics, but the condition of our own existence. The neutron's stabilizing influence also teaches us about fragility. Consider the phenomenon of radioactive isotopes, which are unstable versions of otherwise familiar elements. Carbon-14 with 2 extra neutrons compared to stable carbon-12 is unstable and decays over thousands of years. Potassium-40 present in small amounts in our bodies is unstable because of its neutron-proton imbalance. These isotopes remind us that the neutron's role is not absolute. Stability is a precarious achievement easily lost. The universe is a dynamic place where nuclei are constantly adjusting, seeking the balance that neutrons provide, but not always attaining it. Philosophically, this balance suggests a deeper principle of existence, that stability requires the right mixture, the right proportion, not the dominance of one side or the other. Protons alone cannot make a world and neutrons alone cannot survive outside the nucleus. Only together in measured proportions do they create the diversity of matter. The neutron in this light is a symbol of relational existence, showing that nothing stands alone and that harmony emerges from balance. Modern physics continues to probe the mysteries of neutron stabilization. Experiments with rare isotope beams create nuclei with extreme neutron-to-proton ratios, testing how far the stabilizing power of neutrons can be stretched. The discovery of neutron halos where excess neutrons form a diffuse cloud around a nucleus challenges our understanding of nuclear structure. These exotic systems push the limits of stability and reveal the creativity of neutrons in holding matter together in unexpected ways. At the cosmological level, the stabilizing role of neutrons also intersects with the question of why matter exists at all. In the early universe, the balance between protons and neutrons was finely tuned by the conditions of the Big Bang. If neutrons had been slightly heavier or decayed more quickly, the formation of helium and heavier elements would have been impossible. The neutron's properties, including its stabilizing role, appear to be delicately adjusted for a universe capable of stars, planets, and life. This observation fuels discussions of fine-tuning in cosmology, suggesting that the role of neutrons is not only stabilizing but cosmically essential. The neutron, silent and uncharged, is the unseen key to the most powerful transformations known in nature. While protons define the identity of elements and electrons govern their chemistry, it is neutrons that determine how nuclei behave when subjected to change. Their neutrality makes them extraordinary agents of transformation. Because they carry no electric charge, they can slip past the repulsive electric barriers that protect the nucleus from incoming charged particles. Where protons and alpha particles are turned away, neutrons walk straight in. This quality elevates them from passive stabilizers to active catalysts of nuclear reactions, opening doors that would otherwise remain sealed. The most dramatic example of the neutron's influence is nuclear fission. In heavy nuclei such as uranium or plutonium, the balance of forces is already precarious. The protons strain against one another, their repulsion only barely contained by the stabilizing neutrons. When such a nucleus absorbs one more neutron, it tips over the edge. The added neutron not only increases the instability, but also injects energy into the nucleus, distorting it into an elongated shape. At that moment, the strong nuclear force is unable to hold the opposing ends together, and the nucleus splits apart. Two lighter nuclei are born along with a release of immense energy and, crucially, more neutrons. These liberated neutrons fly outward at tremendous speeds, free to strike neighboring nuclei. If the conditions are right, each fish produces not only energy but more fish events in a chain reaction. This is the principle that underlies both nuclear reactors and nuclear weapons. The difference lies in control. In a reactor, the number of neutrons is carefully moderated so that the reaction sustains itself steadily, providing heat that can be harnessed for electricity. In a bomb, the process runs unchecked, multiplying explosively in microseconds, releasing energy on a devastating scale. In both cases, neutrons are the linchpins of the process. Their numbers, their energies, and their interactions dictate the outcome. The story of how this was discovered is one of the most significant scientific episodes of the 20th century. In the mid-1930s, Enrico Fermi and his colleagues in Rome began bombarding elements with neutrons, exploring the strange transformations that resulted. They found that neutrons could trigger reactions with astonishing ease compared to charged particles. When they turned their attention to uranium, they noticed new substances forming that did not fit existing models. It was only later, through the work of Otto Hahn and Fritz Stresemann in Germany, that the phenomenon of fission was recognized. Uranium nuclei were literally splitting apart. Lise Munner and her nephew Otto Fr., exiled from Nazi Germany, provided the theoretical explanation, showing that the neutron was the trigger for the most revolutionary discovery in modern physics. The potential of neutrons in fission quickly moved from the laboratory to the world stage. The Manhattan Project harnessed this principle to create the first atomic bombs, changing history forever. The destructive power unleashed in Hiroshima and Nagasaki was the consequence of carefully orchestrated chains of neutron-induced fission. It is a sobering reminder that the neutral particle, invisible to the senses, could unleash forces more destructive than anything humanity had ever imagined. Yet the same principle, under careful control, gave rise to nuclear energy, offering power without the need for burning fossil fuels. The double-edged nature of the neutron, capable of fueling both catastrophe and progress, is one of the defining paradoxes of our time. Beyond fission, neutrons also influence other kinds of nuclear reactions. In fusion, the process that powers the sun, neutrons play a different role. Although they are not the primary participants in fusion reactions, the fusion of hydrogen into helium involves protons. The byproducts often include neutrons. These neutrons released at high energies are significant in fusion research today, as they present both challenges and opportunities. In reactors designed to harness fusion, the neutrons carry much of the reaction's energy, which can be captured to generate power. At the same time, their high energies pose material challenges as they bombard and weaken reactor walls. Thus, even in processes where they are not central, neutrons exert a decisive influence. Neutrons also serve as the initiators of transmutation, the process by which one element changes into another. By absorbing neutrons, nuclei can climb to heavier isotopes, sometimes becoming unstable and decaying into different elements altogether. This principle underlies the creation of artificial elements in laboratories. It also governs the long-term behavior of nuclear waste, as neutron absorption can transform isotopes into forms with shorter half-lives, making them easier to manage. In this way, neutrons are tools not only of reaction but of transformation, enabling humanity to reshape the nuclear landscape. On the cosmic scale, the influence of neutrons in nuclear reactions is inseparable from the origins of the elements. In stars, the slow capture of neutrons allows nuclei to grow heavier step by step, forming elements like strontium, beryllium, and lead. In cataclysmic events like supernova or neutron-star collisions, the rapid capture of neutrons forges the heaviest elements such as gold, platinum, and uranium in mere seconds. The glitter of gold on a ring, or the radioactive fuel deep in a reactor core, is testimony to neutrons shaping matter in the most violent cosmic crucibles. Without their role in these nuclear reactions, the periodic table would be truncated and the richness of the universe's chemistry would be absent. Even in everyday science, neutrons are indispensable in probing the structure of matter. Neutron scattering experiments, where beams of neutrons are directed at materials, reveal atomic and molecular arrangements with precision unattainable by other methods. Their lack of charge allows them to penetrate deeply into materials, while their sensitivity to nuclear forces makes them uniquely informative. Thus, neutrons, while central to destructive and constructive nuclear reactions, also act as quiet investigators, helping scientists to unlock the secrets of matter in safe and peaceful ways. The overarching theme in all these contexts is the neutron's neutrality. Because it carries no charge, it is not hindered by the electric barriers that confine charged particles. This neutrality gives it a unique freedom to enter nuclei, to trigger reactions, to sustain chains of transformation. It is the invisible hand guiding the most powerful processes in nature and technology. Whether in the fiery heart of a star, in the controlled environment of a reactor, in the chaos of an explosion, or in the precision of a laboratory, neutrons are the catalysts of change. The influence of neutrons in nuclear reactions and fission is a testament to how the smallest things wield the greatest power. They are reminders that what is unseen can be decisive, that neutrality is not weakness but strength, and that balance and imbalance at the tiniest scales ripple out into the fate of civilizations. The neutron is at once the stabilizer of the nucleus and the spark of transformation. It stands at the crossroads of creation and destruction, a particle that embodies both the hidden harmony and the hidden peril of the universe. When we peer into the hidden world of the nucleus, we find that neutrons are not as stable as they appear. Inside an atomic nucleus, they often act as guardians of balance, ensuring that protons can coexist without flying apart. But outside the nucleus, the neutron reveals its fragile side. A free neutron cut loose from its nuclear bonds survives only about 15 minutes before it decays. This transformation, known as beta decay, is one of the most profound processes in nature, for it shows us that matter is not fixed but in constant flux, and that the identities of particles themselves are not immutable. In beta decay, a neutron transforms into a proton, releasing an electron in a ghost-like particle called an antineutrino. This process is extraordinary because it changes the very essence of the particle. A neutron and a proton differ in electric charge, yet they are nearly identical in mass and structure. Both made of 3 quarks bound together by the strong nuclear force. The neutron contains 2 down quarks and 1 up quark, while the proton contains 2 ups and 1 down. In beta decay, one of the down quarks inside the neutron flips into an up quark, a change mediated by the weak nuclear force, one of the 4 fundamental forces of the universe. In that instant, the neutron becomes a proton, altering the nuclear balance and sometimes even changing the element itself. This hidden ability of neutrons to decay has enormous consequences for the evolution of matter. Consider the origins of the universe. In the first few minutes after the Big Bang, neutrons and protons were formed in almost equal numbers. But because free neutrons decay so quickly, the balance shifted toward protons. This simple fact determined that hydrogen with its lone proton nucleus would dominate the cosmos. The neutrons that did survive combined with protons to form helium during primordial nucleosynthesis. Without the fragile instability of the neutron, the universe's chemistry would be utterly different, and life as we know it might never have emerged. Within the nuclei of unstable elements, beta decay plays another vital role. Many isotopes of elements have too many neutrons for their protons to handle. In these cases, the nucleus undergoes beta decay, converting excess neutrons into protons to achieve a more stable balance. When this happens, the identity of the element changes. Carbon-14, for instance, a radioactive isotope with 6 protons and 8 neutrons, undergoes beta decay to become nitrogen-14 with 7 protons and 7 neutrons. This natural clockwork allows scientists to date ancient artifacts and fossils through radiocarbon dating. What makes this possible is the quiet transformation of neutrons carrying history forward with every decay. The weak nuclear force which governs beta decay is unlike the strong force that binds quarks or the electromagnetic force that governs charges. It is subtle, slow, and yet deeply powerful in its implications. Through beta decay, the weak force shapes the destiny of stars, fuels processes in nuclear reactors, and reveals the fluidity of matter at its most fundamental level. Without it, stars would not be able to convert elements through successive stages of fusion, and the chemical diversity of the universe would stall. Neutrons, by their capacity to decay, ensure that the cosmic story keeps moving forward. Beta processes extend beyond simple neutron decay. In certain nuclear environments, the reverse can also occur. A proton can transform into a neutron through what is called bitup, thus decay, releasing a positron, the electron's antimatter twin, along with a neutrino. This process is equally important, for it shows that the balance between protons and neutrons can shift in either direction. In stars, such reactions are part of the cycles that build heavier elements from lighter ones, linking the neutron's transformations to the grand architecture of cosmic evolution. There is also a process known as electron capture, in which a proton in the nucleus seizes one of the atom's own electrons and converts into a neutron, again releasing a neutrino. Each of these variations highlights how the neutron's hidden potential for transformation is central to nuclear life. The neutron is not simply a neutral bystander. It is a dynamic player in the dance of decay and rebirth, forever blurring the boundary between particles. On Earth, the practical consequences of neutron-driven decay are profound. Medical science uses beta-emitting isotopes to diagnose and treat disease, tracing processes in the body, or delivering targeted radiation to tumors. Industry relies on beta sources for thickness gauges, quality control, and even power in remote spacecraft through radioisotope generators. Every application owes its existence to the neutron's hidden instability, its ability to decay and emit streams of particles that we have learned to harness for human purposes. The mystery of neutron decay also touches on some of the deepest questions in physics. For decades, scientists have measured the lifetime of free neutrons with exquisite precision. Yet, Small discrepancies persist between different experimental methods. These tiny differences have sparked speculation about hidden physics, perhaps the existence of unknown particles or forces beyond the standard model. In this way, the humble decay of the neutron continues to probe the frontiers of knowledge, reminding us that even the most familiar processes may conceal undiscovered truths. Neutrons also reveal their hidden role in the heart of stars through beta processes. In stellar interiors where immense pressures and temperatures prevail, neutrons are constantly being created and transformed. These reactions drive the cycles that build elements up the periodic table. Without the delicate interplay of neutron capture and beta decay, the heavier elements that make up planets, oceans, and life itself would never exist. Our very bones enriched with calcium and phosphorus, our blood carrying iron and the air filled with nitrogen, all are indirect gifts of neutron transformations in the stars. Perhaps most remarkable is the way beta decay connects the tiny and the vast, the particle and the cosmos. The fleeting instability of a single neutron outside the nucleus shaped the balance of hydrogen and helium across the universe. The steady rhythm of beta decay within unstable isotopes writes the history of ancient civilizations in radiocarbon dating. The transformations of neutrons inside stars built the periodic table on which life depends across scales of time and space. The neutron's hidden ability to decay into a proton is one of the engines of creation. The role of neutrons in radioactive decay and beta processes is thus both subtle and immense. They are at once guardians of stability and agents of change, holding nuclei together yet capable of altering the very essence of matter. Through beta decay, neutrons ensure that the universe is not static but evolving, that elements are not fixed but transforming, and that the boundary between life and death in the cosmos is written in particles too small to see. In their hidden instability lies the story of matter's past, present, and future. In the quiet laboratories of Earth, neutrons appear small, neutral, and fragile, but when viewed on the stage of the universe, they emerge as architects of cosmic destiny. Stars, the engines of creation, owe much of their evolution to the hidden work of neutrons. Within stellar furnaces where temperatures soar into millions of degrees, protons fuse to form helium, releasing energy that makes stars shine. Yet, as stars age and grow heavier, fusion alone cannot account for the creation of elements beyond helium. Here, neutrons step into their most profound role. Because neutrons lack electric charge, they can slip effortlessly into atomic nuclei, adding mass and building heavier isotopes without facing the barrier of repulsion that protons encounter. In a process called neutron capture, elements are forged step by step inside stars. Slow neutron capture, known as the S process, enriches nuclei over thousands of years, producing elements like strontium and beryllium. In contrast, the rapid R process occurs during violent cataclysms such as supernova and neutron star collisions, where floods of neutrons bombard nuclei in fractions of a second, creating the heaviest elements in the periodic table, including gold, uranium, and platinum. Every piece of jewelry, every trace of iodine in our bodies, every bit of lead in the Earth's crust owes its existence to the neutron's ability to build matter in stellar foundries. Yet, neutrons do not merely help stars to create. They also decide how stars die. When a massive star exhausts its nuclear fuel, gravity overwhelms its core. Protons and electrons are squeezed so tightly that they merge into neutrons, releasing neutrinos in a burst that heralds the collapse. The star explodes outward in a supernova while the core implodes inward, becoming a neutron star. In this extraordinary object, neutrons dominate completely. The density is so extreme that a teaspoon of neutron star matter would weigh billions of tons. Neutrons, which on Earth are fragile and short, lived outside a nucleus, here form the solid backbone of a star remnant that can spin hundreds of times per second, generate magnetic fields trillions of times stronger than Earth's, and bend light itself with its gravity. Neutron stars remind us of the paradox of the neutron. Invisible and silent in everyday matter, yet capable of defining the fate of galaxies. These stars are cosmic laboratories, showing us how matter behaves at extremes that no human experiment can replicate. When two neutron stars collide, their union ripples space, time itself, producing gravitational waves and releasing torrents of neutrons that seed the universe with new elements. In such moments, the legacy of neutrons is written across the cosmos not in silence, but in bursts of light and energy visible billions of light-years away. Thus, neutrons are not simply neutral particles lost in the shadow of protons and electrons. They are the builders of the periodic table, the guardians of stellar balance, and the architects of the most extreme objects in the universe. From the quiet stability of atomic nuclei to the cataclysmic birth of neutron stars, neutrons reveal their true nature as the silent forces shaping the destiny of matter and the grandeur of cosmos. In the modern age, the neutron has stepped far beyond its role as a silent stabilizer of the nucleus to become one of the most versatile tools in science and technology. Its neutrality, once thought to make it passive, has instead made it invaluable for exploring, probing, and transforming the material world. Because neutrons carry no charge, they can penetrate deeply into matter without being deflected by electric fields, making them uniquely suited for revealing structures that other probes cannot touch. One of the most remarkable applications is neutron scattering. In this technique, beams of neutrons are fired at materials, and the way they scatter reveals the arrangement of atoms within. This has become an indispensable tool for physics, chemistry, and biology. It allows scientists to see how proteins fold, how magnetic materials behave, how superconductors work, and how new materials can be engineered for energy or technology. Neutron scattering, in its quiet precision, has opened entire worlds of discovery, from understanding diseases at the molecular level to designing batteries that last longer and store more energy. In medicine, the neutron plays another surprising role. Neutron radiation therapies are used in certain treatments, especially for cancers resistant to conventional methods. By exploiting the neutron's ability to penetrate tissue and interact directly with nuclei, doctors can target tumors with exceptional precision. Beyond therapy, neutron activation analysis allows scientists to detect trace elements in samples with extraordinary sensitivity, a method that has been applied in everything from archaeology, forensic science. The signature of elements revealed through neutron interactions can tell the story of ancient artifacts, environmental changes, or even criminal investigations. Industry, too, has found the neutron indispensable. In nuclear reactors, neutrons sustain the chain reactions that generate vast amounts of electricity, forming one of humanity's primary sources of carbon-free energy. The careful moderation and control of neutrons allow reactors to run safely, balancing energy production with long-term stability. In space exploration, radioisotope thermoelectric generators fueled by neutron-rich isotopes have powered probes like Voyager and Curiosity, sending human instruments deep into the solar system. Each mission carries at its heart the quiet legacy of neutron processes. Even in the most advanced frontiers of science, neutrons remain central. Research into quantum materials, high-temperature superconductors, and new states of matter all rely on neutrons to probe the invisible. Experiments in fundamental physics seek to measure the neutron's lifetime with exquisite accuracy, searching for signs of new forces or hidden dimensions. Questions about why the universe contains matter at all may hinge on subtle asymmetries in neutron behavior, making these particles key to unlocking mysteries that reach beyond our current understanding. The neutron, once hidden from view and long overlooked, has become one of humanity's greatest instruments for progress in laboratories, hospitals, power plants, and spacecraft. Its influence is everywhere, shaping knowledge and technology in ways both practical and profound. What was once thought to be neutral and inert is now revealed as a particle of infinite possibility, a bridge between the smallest scales of the atom and the grandest aspirations of science.